All right, welcome to reading group or robot learning reading group number 6, I think. Today we'll be doing EgoZero robot learning from smart glasses, presented by myself and Krish Mehta. So before we get started, as always, I'd like to thank our sponsors. We have Palatio and BracketBot. They were kind enough to sponsor the food that you're eating today. So let's dive right into the paper. I think these are sort of like general guidelines I always try to keep in mind while I read the paper. Krish presented some like more specific discussion questions for today's topic, but in general, like when I read over the paper, these are sort of the things I try to think about, like what are their objectives, how was it done before this, what's new in this current approach, and then how do we evaluate the success, and then some limitations. So I'd like you guys to keep this in mind as we go through the paper. So what is the paper about? I guess before we can go into this, if you were here last week, you remember we talked about data collection, right? So currently with robot learning, a very big bottleneck is sort of the data that we collect, right? Because we train these policies on loads and loads of data, and if you collect data very, very slowly, then it's going to take a long time before you train a good enough policy. And we know that these policies require a ton of data. So one big promise is being able to leverage egocentric data, meaning data that's from the perspective of a human. And so this is sort of what they did in this paper. They collected a bunch of data using these smart glasses called Project Aria glasses. And they collect a bunch of demonstrations with their hands. And so this is an example of a demonstration, which is opening the door of an oven with your hands. And what's really promising about this approach is that now we don't need to sort of like teleoperate a robot. We can just wear these glasses and just do a bunch of daily tasks. And then that data is good enough somehow to train your robot. Because again, if you went to last week's workshop or reading group, you would remember that currently the main paradigm is is sort of like this Jello system where there's an operator and he's controlling the robot, and or it could be in front or on the side, and he's basically collecting the demonstrations and just like controlling the robot through this leader setup and leader follower setup. But it takes a long time to set up. It's very constrained, and it's just like there's also this like cross embodiment gap. You like, for example, imagine like folding a T-shirt. It's a lot harder to do it through the setup as opposed to using your own hands. So this is a very promising setup, but to sort of make egocentric work, they had to do a bunch of, there's some like interesting tricks that they did here, right? So why do you guys think that what is the issue if we were just to take this, right? Because if take this data set that we collect with our hands, so these are images, and then we have our hands, and we just like feed this into a policy somehow, and then use it to train like a robot foundation model. Do you think that would work? Yes or no? And why do you think that is the case? Any volunteers?
It's like the human hand is different from the robot hand.
Right. Yeah. And why would that matter?
So it's like, for example, some robot have claws, which is like very different how you.
Exactly. Yeah. So this is sort of the cross embodiment gap, right? So there's a few things here. Number one is, you can imagine this video, right? What you see is a human hand, right? But then you imagine, so the policy or the model you train, it's used to seeing these images. But then you try to deploy this policy on the robot, and what does the robot see? The robot doesn't see a human hand; it sees like a robot arm, right? So that's already out of distribution. And as you mentioned, controlling the robot arm is also slightly different, right? Like we as humans have generally much more dexterity than a parallel gripper. So actually what you notice in this paper is for this specific problem that you mentioned, where like our human hands are much more dexterous, they actually just like collect data like this. And they track these two fingers, the thumb and the index. So you look at the videos, like the entire data set just like this. So this is sort of like how they get around it. And there's like a bunch of limitations that we'll talk about later. But I guess to give you intuition on like, yeah, why it doesn't just work out of the box if you just like train a policy because of this cross-embodiment gap, auto distribution. So we need to get around this. How do we get around this? Well, one way is we want to make essentially, the video. We want to make this agnostic to whether it's a human or a robot. So what they'll do is instead of just feeding your policy or this model the raw image, you're going to choose a better representation. And the representation they use are these 3D points, right? And so here what they do is, I guess in this particular example, what is this, like some sort of pillow? All right, let's say that's your object of interest. What they're going to do is they're going to select a bunch of points, and we'll talk in a second about how these points are tracking, etc. But just assume for now that it works. Like we take a video, there's some pipeline to extract points of interest, and you can track these. So these are like corners of the pillow, for example. You have these points in 3D, and then that's sort of the representation that you feed into your model that you're training. And then you also track your fingers. So this is the action, and this is the state, right? So your state will be like, where is the object in space? And then how you control your arm is sort of the ground truth for that is given by your fingers. And so you track your fingers in 3D space, and you train this transformer. And you do imitation learning, which is essentially just treating whatever demonstration you did as ground truth. And then you train a policy that will predict this ground truth action. And then you run it on your robot. Is there any questions about this process so far? If it's not clear, I can explain a bit more. But there's a few things I mentioned here, right? It's like you need these points are in 3D. So how do you get these points in 3D? And how are these points defined? I think those are like sort of like specific questions that at least I had when I read the paper. So for number one, how they track the points, they use a technique called DIFT, I think is what it's called. And essentially, what this model allows you to do is, let's say, the task is picking up a pillow and moving it somewhere else, right? And you think that the points of interest are like the 4 points of your 4 corners of your pillow, right? So how can we sort of like get these 4 corners? What you can do is you take an image of a pillow and you say, I'm interested in these 4 corners. And then if you run this model, it will just give you, like for a different image, it can just tell you, okay, what is the correspondence? So like these 4 points that I'm interested in, where does it map for this other image that I'm giving you, right? So that's a very easy way to get like these corners for free. But this works in 2D, and then to get a 3D point, you sort of do this process of unprojecting the point. So when they do the inference, getting the point is very easy because they're using an iPhone, and with an iPhone you can just get depth information for free. So you have your 2D point, and then you have your depth map, and then you can just say, okay, this pixel represents, like I know the depth of this pixel, so that's how you get a 3D point. So that's how you do it when you do the inference part. But for training, they use these Project Aria glasses. And so I guess I won't go too in depth, because even myself, I'm not 100% familiar with the specific steps. But in general, it's some sort of like, I think epipolar geometry, and then there's like doing a bunch of math essentially to get back the depth information. It's a more involved pipeline because the glasses just don't directly give you depth. But the abstraction that you use at isolator operator is just they have some way to get the 3D, get the depth of this particular point. So yeah, they do some sort of like solving with epipolar geometry from what I remember, and then there's some ransack in there too, because there's a lot of noise and there's outliers, and you need to filter it out, filter out the outliers. But at the end of this process, you have 3D points, you train it, and then you run this policy. You train a policy, and then you run it on your robot. And it sort of works, right? Is what they show. And I guess, yeah, this is sort of like the table of the results. So they got, that's like around 80% success rate over most of these basic tasks. And I guess what's interesting for me is how does it compare to other methods and these different ablations that they did? So I guess those are more like implementation details, but for example, they needed to do 2D augmentations, which I think perhaps you can get away if you figure out like an even better representation. I guess I don't have a picture of what the 3D augmentations look like, but it's essentially like applying transforms. So you can imagine like if I'm looking at from this perspective and my hand is here and the object is here, if you rotate it like this, right? Like let's say the ground truth is like going like this, right? And you were to rotate it by 90 degrees, you can perform the same motion like this, right? And so that's essentially how they augment it in 3D. You apply these different transforms, and you know the ground truth, right? Relatively everything stays the same, but you sort of like get more data by applying these augmentations. Okay, and yeah, this is sort of like how it works at inference time. You get your diff. You have an object that you're interested in, right? And then you run this diff thing depending on what object you're looking at. So let's say pillow, there's 6 points, and then you track your 6 points, and you get your depth, and then you unproject, which just means go from 2D to 3D. So you have your 3D points, and then you start with, they use a history buffer, but that's basically like what actions you did in the past. And then you compute an action chunk by sampling from the policy that you trained. And then you get your gripper, and then you just run this and update your buffer. So it's quite simple at inference time. And yeah, I guess that's basically how the policy inference works. Any questions on how this process works? Yeah. I think that's mostly it. I don't think it's a very complicated or technical paper, but I think it introduces interesting ideas on how do we get egocentric data to work, right? I think if we're able to scale up this sort of like method and we don't need to rely on teleoperation, then it's much easier to just like scale up the amount of your data collection, right? Like if you give everyone just like these glasses and you ask them to do things, it's much easier than having like a specialized station set up to collect data. So this leads us to our discussion questions that sort of Krish mentioned.
I think we should also still go into a little bit more about like how the points are extracted.
Okay.
Because that's like very important.
Yeah, what do you think?
I think let me add a couple of images. Obviously, I don't think we can go super in depth into the math because the math is crazy. And it's like one of the most fundamental things of computer vision.
Yeah, we can.
I'm adding it.
Like, you think this is important to cover? Like triangulating object key points?
Yeah.
Like, I don't think it's important to cover because you don't need to do it with your iPhone. Like, I think these are just hacks because you don't get ground truth depth, and the depth of your smart glasses are not good enough, so you need to do all this epipolar geometry stuff.
Oh no.
That's my argument.
I think that's more to do with like I think Arya's this version does not have depth, which is why they have to do all of this.
Yeah.
So I guess like the discussion then becomes more on the lines of like, oh, how does like
they could have just wore an iPhone on their head, I think.
They could have worn an iPhone on their head.
And then they would not have this issue.
So the Arya infants they actually use an iPhone.
Yeah, exactly.
But like the Arya training, basically they wear glasses, and glasses have like stereo. They don't have stereo vision. Like it's just like the Arya glasses only have one camera. So and the camera does not have depth. So that's why they do a lot of like interesting stuff with how to identify the point, which basically is the reason why this might not be the most like it's like not the it's very noisy to work with because essentially what you're doing is wait, can you just go back to the slide? Yeah. So like this is something. Can you move to the slide?
Yeah.
So, like, to understand how they're actually getting like the depth is something called epipolar geometry, which is like the basis for almost all of computer vision. But what they do is, like, let's say you had your Oreo glasses, you were wearing your Oreo glasses, and then you had an object in front of you. What they did was they would sample 3 to 5 images, and then basically they would use some sort of like human input to specify in the 2D image where the object is. And once they got one, they used this model called code tracker, which is a basic model to basically track a point in 3D, in 2D. And so they would track that 2D point across the different frames, and then based on the 2D tracked frame of 3 to 5, they would basically do this, where they would have 2 images and they would try to like throw rays to try to get the depth out of it. Because you already know what your camera like extrinsics are, so you can basically tell where the 2D point actually projects in 3D. But to get complete accuracy, you need 2 views at least. So you basically have those 2 views both calibrated, and so now you know that across all these different views, at that 2D point, when you move across them, you get your 3D point. So that's how they got the 3D point, and it uses this model called code tracker. You want to just like show.
Does this have to assume the object is fixed? Like, if the object moves,
Yeah, it does have to assume the object is fixed, which is one of the biggest like limitations for this method.
yeah, it doesn't have code tracker.
Do you want to go to like the demo page? Oh, okay.
Okay.
Classic state of source many times.
This is by
Wait, no,
Facebook.
actually, open up code tracker. Oh, this is 3. Never mind. But like, if you zoom in,
Zoom into what?
like any video, you'll notice how like each of these are basically representing the points and how the points are moving. And so you could select one point specifically on the object. And as the object moves across the video, you would still be able to track it through the video. But the thing is, instead of the object moving, the object is static in our case, the viewpoint of the user moves. Because it's an egocentric view, when they were collecting data, they would move around the object, and they would get those multiple views, and that's how they projected it to get the 3D view. And they would use this model to basically get the 2D points as they move across the frames, and then they would use the different frames to basically project it by throwing rays to get the 3D point. Now this is much harder. How would you make it easier? You would basically have an iPhone which gives you depth by itself. So rather than you having to do all this crazy math, you can just like select the point and iPhone will give you the 3D point. So it's much easier to do it with math, for example.
Okay, I'm gonna give a shout out to my YouTube channel over here, because I actually worked on this over the summer, or a year ago, and I'm not sure like how specifically they did it here, but
Figure it out.
like here's like, this was my attempt at explaining epipolar geometry, where, okay, maybe you should just watch the video, but you essentially track points in 2D and 3D, and you do this. I mean, this is like just getting your point reprojection, and then there's some reprojection error, and then I need to review the math, but you should do this. I don't know. But these are all just hacks. If like, again, if you have an iPhone, I think it's not big of an issue. So, anyways, yeah.
Yeah, so this is how they did the point extraction. And the other very interesting thing was like the morphology. Like, because they used human hands, they could basically extract as many number of key points as they wanted based on the robot that they were training. So for example, in this case, they were training a robot that required 6 degrees of freedom.
Mm-hmm.
And so what they did was they basically used the hand tracking, and usually they would use only the thumb and the index to specify the gripper, because they were training a robot that had a simple gripper, like parallel jaw gripper. But the Oreo glasses are pretty good in terms of hand tracking, where they can give you 21 key points. So like at every thumb and joint, you can basically get 21 key point outputs from the Oreo glass. And so they would reduce those 21 to 6.
They just collected data in such a way that, yeah, it's easy for the robot to learn. Yeah, but so the question that you are starting to ask brings up, yeah, like what are the limitations of this method, right? Because you still need to be, like you can imagine if I just give you glasses and you don't know how robotics work and you just like go out there and collect data, like perhaps this data is not like good, right? And you know, there's things like, for example, many tasks, I don't think they had tasks like this in this example. I can name like 2 limitations right now off the top of my head that I think very obvious. Number one is like how do you deal with occlusions? So let's say I lift like this object. Okay, one is like they're tracking 6 points, for example. If like the points are occluded or your hands are occluded, sometimes you can't track your hand very perfectly. Number two, with just like learning from videos, one of the limitations is that you can't fully learn forces, right? So you can think about like when I'm grabbing this object, right? Like if my hands are like this versus an object in between, I actually my force is actually more like this, right? It's more closed, and so through a video, it's really hard to see like where's the force applied, right? And whereas in your teleoperation setup, you have full access. You can see sort of like the person teleoperating will fully close the grippers, but the robot can't fully close the grippers because there's an object in between. But you sort of like capture the force that you're trying to apply. Whereas in a video, it's like really hard to see that. So maybe for like a lot of tasks, it doesn't matter. But maybe it's like a very heavy object or different cases like that, where it's important to learn sort of like these forces, like the dynamics. Then you can't quite solve that with learning from videos. Are there limitations that you guys can think of, or general sort of thoughts on the paper?
Static objects, like it's just a paper.
Yeah, I think static objects is actually fine. Like in most cases, your thing's not moving like all over the place, right?
It becomes harder to recover from errors eventually. Like what if like the first attempt was to pick up the object, right? And then it managed to fail at doing that, but it ended up moving the object somewhere. If it's a circular object of sorts, then it potentially could be rolling around.
And I'm not sure, like when you say static object, because like when you do the pick and place, the object moves, right? So it's like, it's not like it's fully static. Like you're able to pick it up and move it. So,
like what if it failed at this task right now, and it moved the object?
if it failed here,
Yeah, I failed at picking up the object before it's done. I'm not sure if this system would be robust enough to recover that.
would it not just try it again?
It would have to restart the inference all over.
You have to restart the inference all over.
Yeah.
Because of the algo that they use here.
But they also do augmentation. So it's possible the augmentations, like over here, the augmentations are basically like, for example, once you collect the data set, you could try to move the, like you could translate things by an X amount, or you could like rotate things by a few degrees, and so on and so forth, to basically create a little bit more noise in the data set, to make the data set a little bit more robust. Because you're also only training on like 100 data sets.
Yeah.
Like 100 blocks.
Okay. So they track the points here, and then when they do the rollout, it doesn't get updated?
Yeah.
It's just fixed?
Based on the algorithm, yeah.
I see. So if it fails, you need to rerun this step.
Correct, yeah.
Okay.
So you have to restart from, like, basically it's a new run.
I mean, they could just like plug it in here, but I assume this step takes a long time.
Yeah, because you're also using like other models.
Yeah.
You're reading depth, and getting like the 3D point from iPhone is very quick. Like that doesn't take more than a few seconds.
Yeah.
But you also like to get the depth, you need to get the label first, for which you're using diff. And diff, I don't know how long that takes to run, but obviously it takes some time to run.
Yeah. Any other points or questions or thoughts?
Like generally for like dynamic objects, one method could be basically when you're creating the data set, you could make it such that you add noise in the data set when collecting. For example, if an object is moving, you could try like literally failing the first time, and then like try to go back to collecting that data with the new like position of the object. It's less likely to see dynamic objects, you're right about that, but like generally objects that are kept in place will stay in place and are to do because of motion. So yeah, generally like that will happen, but like you could add more like training scenarios there. I guess like another really tricky part would be deformable objects, because like there's a fixed amount of force that you apply, and like when you're trying to use your hand, you obviously like you're not collecting that data to see how much force you're applying, right? So if the same amount of force is being applied all the time for any X number of objects, then at some object in the future you will reach a formable object that will fail at that certain force that you apply. So maybe an extension of the work would be you have some sort of like tactile sensing, which is basically force sensing. Like you basically put a sensor on the fingers, and then you try to measure how much force was applied to pick up that certain type of object. But then the hard part of generalization then becomes like you have to have a really good understanding of the different kinds of objects that you expect to see. So then you have to really create a bigger data set with multiple different applications, where you have deformable objects, static objects, dynamic objects, you have rigid bodies.
Because I think like it's like kind of overfit on the object you're manipulating, right? Because each object has like a variable number of points that they decided to label themselves, and then like it's depending on, like in the algo, depending on what object you're interested in, you'll like identify the key points with the corresponding like data set, like whether it's like a bread or like an oven, right? You have like, okay, I want you to do something with the oven, so I'll just like take an image of an oven and then run diff, right? Like that's not very generalizable. Like perhaps you could just use like some sort of like mask, like more general, like a SAM sort of approach, and hopefully generalize it to any object. I think that could be cool.
Yeah, I mean, diff is also fairly generalizable because it's not like completely fine-tuned, but it's trained on a larger data set.
Yeah.
But then when you're like clearly like for each task you perform, the task itself is limited to a few types of objects, right? For example, like opening an oven, that's limited to an oven.
Because also I think one thing that's interesting is they had a baseline from affordances. And I think what this means is basically, right, like if you know where your object is, you can sort of like generally just hard code some sort of path for how to do a particular plan. And so for opening an oven, it sort of like works because it's very simple. But for more complex things where the trajectory sort of should be learned, I think, and they talk about this in the paper, where the affordances fail.
Affordances, like the easiest way to visualize is like imagine being able to generate multiple different class points for any object.
It fails on tasks that require complex nonlinear motion, such as put bread in plate and erase board. These policies exhibit incorrect behavior, drags the bread onto the plate and pushes the board with the eraser. Yeah. But yeah, I think concluding thoughts is like, this is a very, I guess like proof of concept that you can somehow leverage egocentric data. And I think there's there's many ways to build on top of this, or like ideas from this, right? Like one is, perhaps you just slap a GoPro on your head and you figure out like a even better representation. I wonder if like ideally, if you're end-to-end build, like you let your model learn the right representation, but that cannot be done. Like, it's sort of like, how do you get the model to learn the right representation that aligns human video with robot video? And that's like not very clear. And so if you just say, okay, use 3D points, then it sort of works. But it's just like, I don't know. In the long run, I don't know if this is going to work out. Like if you just scale this up, like I'm not super sure. And this is the model itself that they use. I don't think it's super big, right? I forgot how many parameters it is, but the actual policy.
Oh yeah, these are small parameter models. Since they're specifically training it on certain tasks, like they can have like a few 100 million parameters at best.
Yeah. Yeah, it's not even using any like diffusion, right? So yeah, it's very simple. Yeah.
I think what would be the final boss of this method would be if a robot lying in your house would be able to just like look at you performing a task, extract the right representations, and sort of like teach itself what to do. But obviously that's like much harder to do because you're not on an egocentric view anymore.
I mean, where is the appeal of egocentric here? Like, let's say you just did third person here, right? You can still track the hand if like the hand is in the view, so the advantage of egocentric here is like not very much like it doesn't even have to be egocentric, right?
I mean, you're not like aligning the camera frames is then the problem.
I guess it's too out of distribution because the points are like so far away.
Yeah. So how do you like transfer that?
I mean,
like extract like poses of the human hand somehow, and then like
just move the camera wherever. You know where the hands are. You just imagine. Okay, imagine the camera's here instead of there.
Yeah.
That would be very easy.
Apply a transform.
Yeah, just apply a transform where the camera, but because it doesn't even see the image anyway, so like it just sees 3D points. Right. So I think actually that's okay. Maybe we should try that. Yeah, but they talk about failure modes too. Maybe that's our last point. Where does it fail? I think. Do you remember reading on this? Failure came from tracking. Failure? No. Limitations. Yeah, diff was the largest source of error. Correspondence encodes pose. The policy is upper bounded by the accuracy of its 3D points. So if this is true, then like if you tried like third person view, like it's gonna be even worse. How accurate your estimates of the 3D points are. Yeah. Cool. Any final thoughts? I would love to hear from you guys. Was it clear? Like you understand everything? There's no questions? Nothing confused you? Yeah, don't like just because you don't know much about the field, like you can ask. Any question is good. There's no such thing as a stupid question.
I'm a little confused about one thing.
Mm-hmm.
What exactly are they extracting from the egos? Is it like just the hand position, like points from a hand, or are they also extracting trajectories as well?
Well, a trajectory is just a set of poses over time. So they extract the pose of the hand over time.
Okay.
Right.
Also, how are they picking like those points, like the important points? Like, is it just 6? Like,
oh, that's a good question.
They do it based on like
Vibes.
get the manual.
Yeah, they manually label it once, I think, or two.
yeah, you just need to do it once based on which ones you care about, and then you just like filter your art.
So it's in the state space. Here.
Basically, you have a state space and an action space.
This makes we first label a set of 2D points. For each expert label points, we use rounding dyno and diff to map its UV coordinates onto the start frame and track these. Yeah. So how many 2D points? I'm not sure.
I think for the objects there were like 6, and for the human hand there were also 6 actually. 4 or 6.
I mean, in the image there were 6, but I don't know if it's for all of them.
I guess like you could also do this based on like objective. For an oven, like you can only track like 2 points on the handle, and for the human, you would still do the 6.
Yeah.
I guess it's just geometry.
Yeah, it's just focus.
Yeah.
It's cool geometry math. Like if you guys are interested, the ransack algorithm is something to look into. Epipolar geometry is something to look into.
No.
No.
No. No.
I mean,
Well,
honestly, like everything has an abstraction. Like you have really good libraries for whenever you're trying to apply these things in code. So technically, you never write like a lot of these things. But like, if you really care about like, these are fundamentals of like computer vision.
yeah.
Structure for motion is derived from epipolar geometry. So structure for motion is like something that's very heavily used in 3D reconstruction. So given a input of camera views.
I guess if you're interested in it, you can look into the stuff. But if you're more like, on the deep learning side and just like modeling, then perhaps that's not the best use of your time. You should spend more time building intuition on, how different architectures work and like, encoder, decoder, like different architectures, like, yeah, not epipolar geometry. But like, because I spent some time working on this, but now I'm more just like deep learning pill, and it's just like, it's more important to like get better at training models and understanding how models are trained. But like, it just depends on what you're interested in. Cool. Any last questions? Yes.
So why did they stop like an iPhone today?
Why didn't they stop an iPhone into your head?
Yeah.
You should know.
Actually,
You didn't ask them when you talked to them? Or?
no. So I work at this lab, like the one that produces paper.
Yeah.
It's funny, I was supposed to actually work on this.
But they're building a company.
Yeah, things went down. But and they were pretty much almost done at the point, so
Yeah.
didn't work too much into it. Vincent and Mary.
Yeah, Mecca is their company. You can read their thesis. I mean, their white paper. I mean, yeah, this builds off on top of. They believe that worlds built around humans. Like you should collect data from a human perspective, as opposed to like collecting robotics data sets, like what people are doing right now.
Yeah, they took this paper out of the lab and basically tried to expand on it, and now they're doing something with that. Very cool people. Very cool stuff. But they didn't snap an iPhone because I think one of the interesting things that they wanted to do was figure out a way to use Aria glasses.
Yeah.
So that's why they.
Why didn't they use like Meta glasses, or I guess they didn't come out at the time, or like.
Aria was just a research review like back then.
Oh yeah, Aria is by Meta. Sorry.
Yeah, Aria is well. Like the newer glasses have one stereo vision now.
Okay.
And I think Aria Gen 2. Can you search that? I think there's a new version of the Aria glasses.
I think there's like more cameras.
Yeah, this one has two.
How much are these? Can I buy these?
No, you can't buy these.
Is it like you have to be like it's a research kit?
Yeah. You have to be a proper research lab to get these.
They can't just buy that.
Corporate partners. Yo, we can be a corporate guys. We can do this.
Why not?
Okay. All right. Cool. All right. Thanks for coming for this week. For next week, hopefully we're gonna be doing a Coral recap by Shiza. Hopefully, fingers crossed. Coral is the biggest robot learning conference on robot learning. Happened in October. She went there. It was in Korea. Gonna give a recap of like what she thought was cool, and yeah, what's going on in the state of the art. So thank you for listening, and I will see you guys next week.